أرحب بالمحاضرين الكرام والحضور من السيدات والسادة، وفي هذا اليوم الثلاثاء المميز يعني الموافق 20/10/2020. Please allow me, Dr. Sabrina, I make a slight introduction in English, in Arabic, sorry, and then you start your lecture. So المحاضرة هذه حقيقة تأتي من ضمن سلسلة من المحاضرات يقدمها قسم العلوم الفلك والفضاء بجامعة الملك عبد العزيز، ولا أهداف عدة حقيقة. من أهم الأهداف استضافة علماء متميزين كما في حالنا اليوم إن شاء الله في مجال علوم الفلك والفضاء، مشاركة ومناقشة آخر ما توصلت إليه علوم الفلك والفضاء في مجالات مختلفة، خدمة المجتمع من خلال التعريف بعلوم الفلك والفضاء، وتسليط الضوء على مبتعثي القسم المتميزين كما سنرى اليوم بحول الله مع الأستاذ رامي السلمي، وتشجيع وتحفيز طلاب وطالبات الماجستير والدكتوراه. نقطة أحب أذكرها هنا حقيقة أنه قسم علوم الفلك والفضاء بجامعة الملك عبد العزيز يتميز بأنه يعني في طلاب في البكالوريوس والماجستير والدكتوراه تقريبا 36 طالب وطالبة في الماستر والدكتوراه، وعندنا الطلاب الذين يحضرون كورسات الفلك يصل عددهم إلى 1400 طالب وطالبة. التخصصات الموجودة عندنا في السبيس داينامكس، الاستروفيزيكس، السولار فيزيكس، جراوند اند بيز observations, cosmology, observational astronomy and space exploration. يعني هذه التخصصات الموجودة لدينا في القسم. المحاضرة اليوم بحول الله تعالى ستتركز على غاما راي ديتكشن اوف هاي انرجي سيليستيال بوديز، والدكتورة سابرينا عينك ستكون هي أول المحاضرين، وهي محاضرتين حقيقة، الدكتورة سابرينا والأستاذ رامي السلمي. بس مقدمة، I'm gonna make an introduction in English, Dr. Sabrina. Dr. Sabrina is observing the extreme gamma ray universe for more than 10 years, and she expanded her interest to the utilization of machine learning approaches to combine a variety of multi-wavelength data of active galactic nuclei. This led to her PhD thesis with the title of the PhD thesis, The Data Mining Guide to the Galaxy. According to the German Physics Society, it has been among the best in Germany in 2017, and we congratulate her for this achievement. After finishing her PhD studies in Germany, she moved to Australia and now supports the University of Adelaide as a postdoctoral research fellow and commissioning scientist for the future Cherenkov Telescope Array. Her research interests range from cutting-edge data analysis techniques and artificial intelligence to active nuclei and the search for the origin of the highest energy cosmic ray in our galaxy. So I welcome you, our lecturers, and let's start with Dr. Sabrina. Kindly, please.
Yeah, thanks for the nice introduction, and thanks for giving me the opportunity to give this talk here. So I'm going to give you an introduction to gamma ray astronomy. And to do that, I will tell you a bit about the history of gamma ray astronomy. And don't worry, it's a quite young field. I hope it won't be too long. Just digging a bit then into what gamma rays actually are, how we can detect them. And then I'll finish with the future Cherenkov Telescope Array, what the concept is and what kind of science we want to do. So in general, how do we actually study cosmic objects, like, for example, active galactic nuclei? To do that, we can use different messengers. For example, cosmic rays, as protons, for example, or photons, neutrinos, or gravitational waves. So through all these messengers, we can learn something about the object we're interested in. And there are different ground and space-based telescopes to actually measure these messengers. So some of the objects we are interested in are, for example, supernova remnants, if we talk about galactic science. On the left side here, you can see an image of the very popular Crab Nebula. And on the right side, you see what this object is actually emitting. So on the x-axis, the energy, and then on the y-axis, just the amount of flux, the amount of radiation we see from this object. And when we see that this object is radiating in a huge energy range over a magnitude of an energy. And the same is true if we go to extragalactic science. A typical object we're interested in are blazars. Blazars are a subclass of active galactic nuclei. And also these objects radiate gamma rays in a huge energy range. So to summarize, in general, we want to measure these so-called spectral energy distributions, which means amount of flux times the energy square versus the energy, and they all radiate in this huge energy band. So just keep this in mind, since I'm using this in the following as an orientation in the spectrum. So the most intuitive way to observe the sky is probably by our eyes, or a bit more professionally by optical telescopes. And the band, or the energy range that we can actually observe with optical astronomy is quite limited, as we can see here. So with just optical astronomy, we could just measure a very, very tiny fraction of this radiation. And that's where multi-wavelength astronomy comes into play. So the different bands ranging from in the lowest energy from radio over microwave to X-ray, and then the highest energy range is the gamma ray part of the spectrum. And that's a part that I am most interested in, and that's what we will talk a bit about in the following, how to actually measure these parts, this very high energy parts of the spectrum. So let me just go a bit over, tell you a bit about the history of gamma ray astronomy. Gamma radiation was discovered in 1900 by a French scientist, Paul Villard, when he discovered gamma radiation from a radioactive decay. Like 50 years later, the first theories popped out that gamma rays should also be produced in our universe. But then it took, so what are actually gamma rays? So gamma rays is electromagnetic radiation that can stem from different processes, from radioactive decay, but also from Bremsstrahlung, inverse Compton scattering, or synchrotron radiation. And in general, it's an ionizing radiation, which means it has a high penetration power. And because of this high penetration power, it can actually damage bones and organs and so on. So it's actually quite hazardous. So do we have to be afraid of these gamma rays? And luckily we don't, because our atmosphere is actually protecting us. So what you can see here, you can see the opacity of our atmosphere versus the energy, or versus the wavelengths. And you can see that here in the range of gamma rays, the atmosphere will not let through any of the gamma rays. So it's good for us, for humans, but it's bad for astronomers who are interested in this radiation, because we cannot measure it from Earth. So the first detection then of gamma rays from the universe was by a satellite in 1961, which was the Explorer 11 satellite. And this method is still being used. The current satellite that's measuring gamma rays is the Large Area Telescope on board of the Fermi satellite. Here on the right, you can see a sketch of this satellite. And here, this box is the actual detector, which has a size or volume of roughly 1 cubic meter. And here you can see a sketch on how this detector actually works. So it has a tracker to track the incoming gamma ray, to reconstruct the direction, to determine where it's actually coming from. Then it has a calorimeter to reconstruct its energy. And then it's surrounded by a so-called anti-coincidence detector. This is to veto other particles, cosmic rays, like, for example, protons. And with this satellite, with these space-based detectors, we can typically measure the energy band that is highlighted here, which is an energy range from roughly 20 MeV to 300 GeV. And as you can see, we can still not measure the entire range that we are actually interested in. So we still need to go higher to the highest energies. Okay, so here you can see how the sky actually looks in this energy range, in the MeV and GeV gamma ray range. This map that you see here has been measured by Fermi, and it roughly detected 3,000 gamma ray objects. And I just highlighted a few of them. So in the center, we see the Milky Way. Then on the right, you see some famous pulsars, Geminga, Vela, the Crab pulsar. And then here on the top, you can see Macarian 421 and Macarian 501, which are the brightest and closest active galactic nuclei to us. And therefore, they are being studied intensely. So we still want to go through the highest energies, and to actually do that, we need a few ingredients. So the first ingredient that we need for that was the discovery that cosmic radiation is initiating air showers. So when they penetrate our atmosphere, they will create an air shower. This was discovered in 1939. So you see this here. So both gamma rays, but also hadrons, like, for example, protons, will initiate these air showers. The ones initiated by gammas, the processes involved pair production and Bremsstrahlung, while for the hadron, we have many more processes involved and therefore many more different particles. The next ingredient we need is the discovery of the Cherenkov effect. So the Cherenkov effect is when that charged particles that are traveling faster than the speed of light in the medium emit an electromagnetic radiation, and we call this radiation Cherenkov radiation. So we have here this air shower, and this air shower is creating this Cherenkov light, and it's typically in this cone of light. So they used this in '68 when they built the first so-called Cherenkov telescope, where they simply put a telescope inside this light cone. This telescope had a mirror of 10 meter diameter and a camera with 1 pixel. So with 1 pixel, you can only see that there is sometimes more light and sometimes less light. But they did trigger events, but that was basically it. So they were able to prove that there are cosmic rays, but they couldn't discriminate between gammas or cosmic rays, and they couldn't determine the direction or any source of gamma rays. So then it took almost 20 years until the first imaging Cherenkov telescope was developed. And these telescopes already look much more fancy, and they actually had a camera which 37 pixels. And with these 37 pixels, you are able to actually get an image. And from this image that is depicted here, you see an image of the shower, and you are able to reconstruct the energy of the shower and the direction of the shower by the major axis of this ellipse-like feature. So with these improvements, they were then actually able to differentiate between cosmic rays and gamma rays, and also to reconstruct the energy in the direction. And that then led to the discovery of the first galactic object and the first extragalactic object in the TeV range. The first galactic object was the Crab Nebula, which is a supernova remnant, and the extragalactic one was one of the Macarians, which is an active galactic nuclei. In the following years, then they improved the analysis and the technology by starting a stereoscopic system, which means instead of just one telescope, you actually put several telescopes in this light cone. And this had the advantage that you have two of these images, and the intersection of the major axes actually gives you a much more precise reconstruction of the direction. So with these improvements, more and more sources could be detected. And this technique is still being used, and the currently operating observatories are the MAGIC Observatory in the Northern Hemisphere in La Palma. Then also in the Northern Hemisphere in Arizona, there's the Veritas with 4 telescopes. And then in the Southern Hemisphere, there is HESS with 4 telescopes. And the gamma ray sky in TeV energy basically looks like this. So here indicated the objects that we were able to measure. We talk here about roughly 200 gamma ray objects, and in the color indicated what kind of objects we actually were able to measure. And the red dots, which are the mostly extragalactic ones, are the AGNs. And then on the galactic plane here, you see lots of sources ranging from supernova remnants to pulsar nebula and pulsars. So the new era of gamma ray astronomy, the future, is the Cherenkov telescope array. And this will be huge compared to what we have currently. It will consist of 2 sites, one in the northern, one in the southern hemisphere. And it will have more than 100 telescopes. And with these telescopes, we will achieve an unprecedented sensitivity, and we will be able to cover an energy range from 20 GeV to roughly 300 TeV, or even higher. So just to show you or tell you a bit about the people involved in this project. So it has more than 1,000 members, more than 200 institutes from 31 countries. One of them being Australia, and there are 6 universities involved, and the University of Adelaide is leading these efforts. So I'll just quickly introduce you a bit to the Cherenkov telescope array. So it will consist of 3 different types of telescopes. There are the large size telescopes, and as the name suggests, the biggest ones, with a mirror diameter of 23 meters. And they will be responsible for the lowest energy range, ranging from roughly 20 GeV to 3 TeV. They are responsible for the low energy range because they have this large mirror. The larger the mirror, the more light you can collect, and therefore the lower the energy you can go, because the lower the energy, the less light this shower will produce. Here you can see a few pictures of the prototype, which is being built in La Palma. In 2017, they started building the foundation, and then in 2018, they installed the mirrors. And they actually also inaugurated the telescope in 2018. And now they are actually taking science data and were able to detect the first source. So that's pretty amazing. The other telescopes are the medium-sized telescopes, which are a bit smaller and responsible for the medium energy range. And then there are the prototypes. You can see here the structure being built in Berlin and 2 different cameras being built in Heidelberg and Paris. And then there are the small-sized telescopes, which are responsible for the highest energy range, ranging from 1 TeV to 300 TeV. And we will build roughly 70 of these telescopes. Here you can see the prototype, which is in Sicily, in Italy, and the camera we built for that. It's a very special and new design that we are following for the small-sized telescopes. As you saw before, the large and the medium-sized telescope, they had 1 mirror, and the light was directly reflected from the mirrors to the camera. The small-sized telescopes are being built in the so-called Schwarzschild-Curie telescope design, which means that they have 2 mirrors. So they have a primary mirror, which will focus the light on the secondary mirror, and this mirror is then focusing it on the camera. And this has some advantages when it comes to resolution. And that's also the reason why the cameras for these telescopes will have more than 2000 pixels, because we can actually make use of that, and we will get very refined images, and therefore improve the reconstruction a lot. So a bit about the 2 sides. So we have the northern side, where we will build 4 of these large telescopes and 15 medium ones. From the northern side, the plan is to mostly observe AGNs, and that's why we are totally fine not going to the highest energies. On the southern side, which is going to be in Chile, we will have much more telescopes. So we will have the 4 large ones, and then 25 medium ones, and 70 of the small ones. And the small ones are spread over a huge area. And by that, we are just increasing our detector volume. And that's very important because events of the very high energy are very, very rare. And that's why detector volume is very important. So here you can see a bit on the expected sensitivity and performance that we are expecting compared to recent observatories. So here you can see MAGIC and HASS, which are currently operating telescopes. And here you can see the Fermi sensitivity. And you see here with CTA, we will improve the sensitivity by an order of magnitude. And the same is true when it comes to angular resolution. Again, here, current operating telescopes, Fermi, and this is what we expect with CTA. And high-end resolution means we can learn much more about sources, especially about extended galactic sources. So if you're interested in the science that we want to pursue with this Cherenkov telescope array, I would recommend you to have a look to this book, which is available on the archive under this link that I can post later on in the chat. And there we are introducing the key science projects, which are ranging from a project about the galactic center and the galactic plane survey, but we will also perform an extragalactic survey, and you're interested in pavitrons and much more. So I'll just quickly go through a few of them. So one very interesting one is a Large Magellanic Cloud survey. And that's especially interesting because it's an active star-forming galaxy, which means we expect, or we think there are more than 60 supernova remnants and hundreds of H2 regions. So that's a lot of going on, and therefore very interesting to study. Here in the middle, you see how it currently looks for Hess, and there's not much more. And here on the right, you see what we expect to see with CTA. So this is a simulation. But with this improved sensitivity and angular resolution that we saw before, we should be able to resolve it like we see here. So that will be very interesting. Then when it comes to transients, so with transients, they are different events. There are gamma ray bursts, but there are also neutrino transients or gravitational waves, or just flares from AGNs, for example. And we will follow these up, and with this improved sensitivity, we can learn much more about them in a much shorter time. Yeah, then there are AGNs, and one question that is still not fully understood is what is actually powering AGNs, if it's powered in a hadronic or in a leptonic scenario. And as you can see here on the image, in blue, the hadronic model and the leptonic model, and in white, the current data points we have. And as you can see from that, we cannot really distinguish which one is true. But if we have CTA, we will have a much finer resolution of the spectrum, and we will be able to actually distinguish between these quite similar scenarios. And yeah, that's just an interesting question to figure this out. AGNs are also highly variable, and from this variability, we can learn a lot about the processes going on. And that's why we need this sensitivity on very short timescales. And you can see what we might be able to do here, also from a simulation. Then there will be a galactic plane survey, and this is also, again, a simulation of how we expect the galactic plane to look like, and you see lots of supernova remnants here. And that will be very interesting for Rami, who will talk after me and go into that. And then in general, we are just not sure how the extragalactic sky actually looks like, because currently we only have targeted observations. So what we want to do is a blind survey where we really in an unbiased way observe the sky. Yeah, so just in the thinking about time, I'll just go over that and just finish up here with a summary. So we have the Cherenkov telescope area coming up, which is the future of gamma ray astronomy, and with its unprecedented sensitivity and resolution, we will get a new view into physics, and we developed a quite exciting science program, and there will be a lot of science to study from those results. CTA will be operated as a proposal-driven open observatory, which means it is open access, and it has a guest observer program, which means at some point you might be actually able to observe your source and benefit from CTA. And with these 100 telescopes, you can imagine we will produce lots of data in the order of 100 petabytes. And currently we are building it. You saw that the prototypes are being built, and right now we are preparing the sites and the mass production of all these telescopes. So yeah, and I would say it's the start of a new era of gamma ray astronomy, and we are all very excited here about what to come. All right, thanks.
Great. Thank you very much indeed for this amazing lecture, and very useful, since lots of information will be gathering via gamma ray detectors and via CTA. Thank you, Dr. Sabrina. And we will let the questions after Rami talk. If you don't mind, I will introduce Rami. He is one of our postgrad students in Australian Institute of Physics under the supervision of Dr. Sabrina. Sorry, I'll switch to Arabic, Dr. Sabrina. يعمل على الماشين ليرنينج، هو العمل تدقيق من خلال الكمبيوتر لبحث العلاقة بين الأرصاد في 3 مجالات اللي هي الراديوي والضوئية والغاما راي. وهو حقيقة رامي من طلابنا المتميزين والنشطين حقيقة، وسيقدم التوك عن دراسات وسط ما بين نجوم الأجرام ذات أشعة غاما. فليتفضل الأستاذ رامي.
السلام عليكم. بسم الله الرحمن الرحيم. اليوم بإذن الله حنتكلم. Thanks for Dr. Sabrina first, because that's introduced the talk for me and prepare everything to talk to the people here. I will mix my talk because there is some people here in English and Arabic, so I'll try to make it both in English and Arabic as possible as I can. So في الدراسة, in our studies here, we did ISM studies of gamma ray sources. So in Arabic, basically, we درسنا الأرصاد للجاما راي خلال الجلاكتيك بلين مع أرصاد أخرى من الأوبتيكال ويفلنت H alpha focused in my project in the masters. في الماستر احنا ركزنا على H alpha. What I will outline here, التوك حقي حيكون حبدأ بالسوبرنوفا، بعدين حتكلم عن السوبرنوفا structures، بعدين حروح his observations as Sabrina mentioned، بعدين حتكلم عن H alpha observation for sky، بعدين حتكلم عن الميثود اللي احنا استخدمناها، أخيرا حاصل للresults اللي طلعت في الماسترز، and lastly in conclusion. So as we know, everyone here in English or Arabic, that supernova created when stars collapse, when the hydrostatics equilibrium have a problem in the stars after it's running fuel. So بعد احتراق الهيدروجين عندنا هيليوم، بعدين السي شن، الى ان يصل ستار الماسيف. طبعا معظم السوبرنوفا تكون في الماسيف ستار سيلر ماس اكبر من 8 سيلر ماس. فبعد ما ينتهي الفيولز داخل الستار تصل للايرونز، ما في اي انتراكشن ذا، فيصير unbalance in the hydrostatics ويصير السوبرنوفا. في السوبرنوفا يصير عندنا shock in the front shock and back shocks, which is make something we know في الفيلد حقنا as a supernova remnant. Supernova remnants is really interesting because we observe it in many things, but there is many types of supernova, and that affects supernova remnants. So we have type IA and type IB and type 2 with different types on them. Some of them like have a hydrogen, as in type 2, which is mainly we know that this supernova is type 2 by the existence of hydrogen line in the supernova. إذا وجدنا الهيدروجين في السوبرنوفا يعني نعرف إنه هناك في type 2 supernova. طبعا برضو الراديو observation تكون واضحة في type IB و type 2L. في عندنا ejection velocity ثابتة للكل. الانرجي most of the supernova have energy 10 to the 51 erg as initial energy. That's a massive energy. So after that we will go to the SNR. So as Dr. Sabrina mentioned before, مثل ما نعرف إنه المثال الأكبر للسوبرنوفا remnants هي الكراب نيبولا. الكراب نيبولا مثل ما نشوف هنا في السلايد تم رصدها بجميع wavelengths. Sabrina showed some image before, and this is also another image with radio, infrared, optical, and X-ray and ultraviolet. So these objects وهذه الأجرام السماوية لامعة وواضحة للكل. فهي شيء نهتم فيه لدراسة تكون العناصر الثقيلة، لأن معظم العناصر الثقيلة فوق الأيرون يتكون من السوبر نوفا والسوبر نوفا elements في الشوكس. فيصير shock acceleration and high elements created. So it's really interesting for physicists to know more about these things. And Crab Nebula is one of the most interesting sources over the fields, and it's also measured most of the luminosity in the supernova are measured by the Crab Nebula percentage. We will go to next, HISS observation. So high energy spectroscopy systems use circumferential radiation, as Sabrina mentioned. Detection methods, there is 5 telescopes in HISS, 4 small telescope and 1 large telescope. So as that difference between the energy band, so as the telescope detect more. So the smaller telescope, I think if Sabrina maybe remember that, I think the smaller telescope for high energy and the larger telescope for lower energy. That's what I remember, I think, if I'm not wrong. Detection, this graph here showing illustrate for the detection of the gamma ray. So the gamma ray, when it's hit the atmosphere, the change in the speed of light between the space vacuum and the atmosphere create a Cherenkov light. And that light will last for milliseconds, small amount of time. So we need a telescope with high velocity shutter speed or high cameras that can capture these lights. And HISS one of the telescopes that do this, and this the resolution of HISS is almost 0.1 degree. الدقة حقت التلسكوب 0.1 degree, تقريبا 6 arc minute in the sky, which is good. يعني احنا قاعدين نرصد high energy بدقة 6 arc minute، يعني قاعدين نشوف شيء very high resolution. So in 2015 and 2018 also they published HISS observations published as a sky map for all the sources in the galactic plane. So this is all the sources have been detected by HISS in the galactic plane, and it's from 70 degree plus to 250, and it's not from like 70 started, it's contained the galactic center. So from 0 to 70 and minus almost 100 or minus 120. So that's contain all the galactic plane and most of the sources that have gamma ray. يعني معظم الأجرام السماوية اللي في الجلاكتيك بلين تم رصدها بالهيس ورصدوها، وهذه الصورة موجودة، والويب سايت اللي موجود تحت برضه I will send the website link for this paper, so you can just download the fit file if you want to do work on it back home, or you can download this image to count the sources. So there is a lot of sources in this sky survey, and there is some issues with this sky surveys because we see in many sources, but at the same time we have a problem because we don't have some information about some of the sources. So this here illustrates that we observe around 78 or 76 sources, almost an 80 source in the galactic plane. However, more than 50% of these sources are not identified well. So ما نعرف من فين جات، ما نعرف إيش السبب اللي why we observe these gamma ray sources. However, we have some indication. عندنا بعض indications حتكلم عنها بعدين, but we don't have a really solid conclusion about these sources. So some of the sources we have like 8 supernova remnants, one of them like Crab Nebula, and we have another 2 or 3 others. We have a pulsar wind nebula, 12 pulsar wind nebula known that produce gamma ray. And we have 8 composite and 3 binary systems, and one of them I have work in it. I will tell you about it later. حتكلم عنه بعدين. طبعا شغلنا حيكون حنركز في البروجكت حقنا انه كيف ندرس ال 50% or more than 50% in these galactic plane and other wavelengths, so we can try to investigate them and try to find a conclusion about where they came from. So I used another sky survey with the HIS, which is H alpha. So H alpha is very well-known optical line. It's also illustrate the ISM gas gas intensities and how is the gas how is the warm gas in the galactic or in the sky are structured. طريقة تركيب الغاز في الجالكسي. ف H alpha line is very interesting optical observation because it can show us some of the hints about supernova remnants. These hints will help us to link his sources to the H alpha remnants. I will conclude about it later. And another key in this observation إنه there is a relation, في عندنا علاقة في ratio between H alpha and S2 that if إذا كانت larger than 0.5 relation between the intensity حقت H alpha على silver line that's conclude that this observed feature is of cloud is a supernova. طبعا هذه دراسة خذناها وخذنا الميثودولوجي. سوينا الميثودز constructing the method that we will work in. So we will scan for an undefined source, as I mentioned, إنه إحنا حنشتغل على sources that not identified well أو غير معروف الأساس حقها. في الHIS Galactic Plane Survey, I show you before there is like almost 40 or 42 sources that not well identified. So احنا حنستخدم برضو optical observation from H alpha, and also we used other radio observation and gamma ray sources to search for any similar morphology or structures. احنا عندنا structure من الجاما ray وعندنا structure من H alpha، فهذا يعطينا similarity. فإذا كانت في similarity يعني في connections. احنا برضو حطينا في الconsideration حقنا انه نشيل الولفرايت and H2 region اللي هي high intensity in H alpha، وممكن تسبب لنا مشاكل في البرودكشن لأنه ممكن نرصد cloud أو emission from H alpha but it's well known H2 region أو wolfrite. So كذا we took this and plot them in our plot to know if there is if these clouds are related to H2 region or wolfrite. And lastly, we use some SNR model and stellar wind model, which is I will present now. So we use this equation, which is a simple equation, to find the radius through iteration in the time. So we have احنا عندنا الايكويشن هذه شغالين على so dt وهو التايم change اللي هو قاعد time for each radius. So عندنا time وعندنا radius وعندنا initial velocity which is almost known. عندنا density of the ISM which was we consider 0.1 centimeter cube for the galactic plane because there is a study mentioned that the density of the ISM is almost around 0.1 centimeter cube. And we predict some initial mass for the progenitor stars that we will expect later on. So this equation taken from this paper, 2013. And also we use a stellar wind bubble to create a prediction for each from morphology or structure نعرف ايش قاعد يصير في الشكل اللي قاعدين نشوفه او الفينومينا الظاهره اللي قاعدين نشوفها. اذا سوينا تطبيق للاتش الفا وسوينا تطبيق للجاما راي نشوف ايش قاعد يصير من خلال تطبيق المعادله السابقه اللي هي supernova remnants radius and age and stellar wind model. اذا استخدمنا العلاقتين هذه وطلعت في تشابه بين العلاقات والمورفولوجي حقت الجاما راي والمورفولوجي حقت الاتش الفا، هذا يعطينا conclude that this phenomena is related to the his source. So here we have a Maslow's rate from the initial star with the velocity, and we have the initial luminosity winds in Earth. So in this project احنا اشتغلنا على الأجرام السماوية هذه. طبعا as you see here يعني انتم قاعدين تشوفون هنا انه there is a distance and there is age. However, this distance and this age are from the suspected pulsars for these regions. So there is a pulsar star. So how we can say this gamma ray came from supernova? So if we cannot say this unless there is a pulsars there that have been exploded and turned to pulsars. The pulsars اللي هي neutron stars have been exploded. فيه الأجرام السماوية هذه موجود فيها suspected pulsars that literature الناس تكلموا عنها قبلنا وقالوا إنه هذا الجرم أو هذا البلسارز متوقع إنه يكون السبب الرئيسي للجاما راي هذه، بس ما في أي إثبات للعلاقة بين البلسارز والجاما راي. ولكن مع دراستنا للاتش الفا واستخدام الايكويشن حقت السوبر نوفا موديل والستيلر ويند موديل ان رؤيه علامات في الاتش الفا we can conclude that نقدر نقول هذا النجم وهذه الظاهره في الاتش الفا لهم علاقه، بما انه النجم هذا عمره 200 سنه وحتكلم عنها في الريزلتس انا حانتجها الحين. However, this is the result here. So first of all, I start to plot all the sources of gamma ray. رسمت كل الجاما راي اللي موجودة عندي في ال Galactic Plane Surveys ووضعت الكونتورز حقتهم على ال H alpha as a first introduction. So رسمنا كل الكونتورز حقت الجاما راي على ال H alpha بحيث أن نطالع في الجاما راي ونطالع في ال H alpha ونقول هل هناك في علاقة؟ هل في شيء؟ هل في features as we see here؟ يعني احنا نقدر نشوف الحين في السلايدز هذه انه الجاما راي لها مورفولوجي، بعضها كروية، بعضها سفير، بعضها lines، فهذا يعطينا indication in the H alpha that there is a relation. If there is a relation it should be similar morphology to the gamma ray، يعني انه العلاقة بين الاثنين حتكون متشابهة. And as a result for this one, for this scan, we start to find this source, which is a history 1356 and 654. So this source is really interesting because, as you see in both images, there is an H alpha luminosity. في إشعاع من ال H alpha. طبعا السورس هنا مرسوم باللون الأخضر، الكونتورز حقت السورس بالجاما راي. الصورة اللي فوق راسمين معظم ال H2 region، والصورة اللي تحت راسمين الولف رايت، على أساس نبعد عن ال H alpha emission اللي واضحة تحت الصورة، واضحة هنا، ما أدري إذا كان شوف الموس، بس واضحة هنا إنه في there is emission in H alpha, but there is no H3 region and there is no wolf right related to this emission. إنه ما في أي علاقة بالemission هذه بأي source ثاني. فهذا أعطانا indication إنه ممكن هذا السورس interesting، ممكن إنه نبدأ نشوف إيش قاعد يصير مع السورس هذا. فأخذنا السورس هذا للمرحلة الثانية، طبقنا الموديل عليه، طبقنا السوبر نوفا ريمنانس عليه. طبعا طبقناها على البلسارز اللي هو PSR J1357 -6429 which is indicated in the center of this source, almost in the left center. طبقنا على الموديل استخدمنا العمر اللي موجود في الجدول السابق اللي وريناكم اياه، واستخدمنا الديستنس اللي هي تقريبا 2 to 2.5 كيلو بارسك. نتج عن هذا supernova remnant sphere or shape from the model, which is overlap with the supernova, which is overlap with the H alpha, or partially overlap with H alpha feature. يعني بشكل غير مطابق كليا ولكن مطابق جزئيا مع ال H alpha. فهذا أعطانا indication إنه ممكن ال H alpha features هذه related to this source. طبعا هذا السورس الأول. دخلنا في السورس الثاني. طبعا الانترستنج في السورس هذا إنه in the upper side of this source we can see there is some similarity. احنا هنا سوينا استخدام للراديو، سوينا استخدام للإتش ألفا، بما إنه there is أنا استخدمنا الموديل اللي هو في الداخل باللون الأورنج الخافت اللي هو supernova remnant، وفي الخارج اللي هو باللون الأخضر الخافت اللي هو stellar wind bubble. فحاولنا نوجد علاقة، ولكن في هذا السورس هناك حاجتين أساسية. أنه أول شيء السورس هذا مرة خافت، حتى في الجاما راي إذا كنتوا شايفينه في الجاما راي الحين اللون الأحمر الغامق هو اللي نراه في الجاما راي with 5 sigma level. اللون الأحمر الداكن هو اللي 3 sigma level, which is we cannot يعني ما نقدر نكون معتمدين على 3 sigma لأنه الconfident level حق 3 sigma أقل من 5 sigma, which is parameter where you can say there is something the definition level. But الشيء المهم هنا إنه في lines in H alpha in the lower bottom here, in the left lower of this source, which is also overlap with 2 H2 region. احنا شغالين على السورس هذا والحين قاعدين نحاول ناخذ ال H2 regions هذه بدقة أعلى. السورس الأخير اللي حنتكلم عنه هذا السورس، وهذا مرة مهم، وأقول لكم ليش مهم بعد شويتين. طبعا أول شيء هذا السورس هو كان الانيشيال بروجكت حقي. هذا السورس تكلم عنه فابين one of the students here اللي هو الطلاب اللي أخذ دكتوراه قبلي. هو اكتشف العلاقة بالعلاقة ال H alpha اللي تحت هنا as a supernova to this source in the gamma ray. يعني هو اللي اكتشف إن السوبرنوفا هذه لها علاقة بالهيس سورس هذا من خلال استخدام المعادلة السابقة اللي فوق. هو اكتشف هذا الشيء ونشره في 2016. فأنا جيت بعدين ومشيت على السيرفي كامل، يعني هو اشتغل على الأوبجكت هذا وأنا اشتغلت على السيرفي. ولكن الشيء المهم والأهم من اللي هو سواه إنه في structure في الصورة. أتوقع لو قريتوا الكابشن حتقولون موجود الستراكشر. there is a morphology of jet, and this jet is really interesting because we have a microquasar and احنا عندنا binary systems which is in the bottom here, the mass, where is the point in the mass here, and that microquasar is one of the energetic source in the galactic plane. So it's high energy source. It's believed to be having some radio jets before, but there is no certain about it. Also, now a paper published in 2 months ago suggesting that there is a magnetar in there. The magnetar معناه إنه there is a neutron stars مع high magnetic fields, which is indicate also إنه فيه hypernova ممكن، اللي هو hypernova where is you create 2 jets from the hypernova. طبعا هذا حيكون آخر شيء في الريزلت. الأوبجكت هذا إحنا شغلنا عليه كثير مع الدكاترة يعطيهم العافية، Gavin, my primary supervisor Sabrina, and we have now a paper that will be published soon inshallah بإذن ربي about this source with the contribution from Gavin, Sabrina and Tiffany, which is one of our students here, and also other people. Hopefully it's in the last stage, so next 2 months, inshallah, Allah yassir. And that's the time for me, I think. Thanks for everything.
Great. Thank you very much, Rami. Very interesting. And I think the paper will be published in the monthly notes, is it?
Yeah, Manras. Yeah.
This is one of the ISI journals. That's great. Thank you both for the excellent, nice lectures we had. And kindly, if there are any queries and questions, please, we have lots of pioneer professors with us in this meeting. Till they prepare their question, I have a question to Sabrina, please. You hear me, huh?
Yeah.
Right. Actually, your wonderful lecture and presentation enlightened us about the importance of gamma ray observations, either from ground-based or space.
Mm-hmm.
But you talked about the CTA and the new era is going to start. I understood from your talk that there are 3 sites now in Chile, Spain, and Arizona. Is that right?
No, there are 2 sites. One in the northern hemisphere, which is in La Palma, which is the Canary Island of Spain, and in Chile, in the southern hemisphere. Arizona is the Veritas telescope, which is currently an operating telescope. But CTA will have just 2 sites, but yeah.
Excellent. And as you mentioned earlier, there will be more in the near future. Lots of the CTA telescopes.
Yeah. So that in Chile right now, we are still preparing the site. So building roads. So that takes a bit, so it's a bit delayed. But in La Palma, since it's built next to MAGIC, the other telescope, we already have the infrastructure. And that's why building the telescopes is in a much more advanced state and will be, the telescopes will be ready much earlier. So we have already one of the large ones. So, and with that large one, we can already do very interesting science.
Yes, absolutely.
For the other ones, John, yeah.
That's right. Because we actually have a telescope in Chile, Paranal, for observing exoplanets. And I know how difficult it is to construct the telescope and the road as well. But it's one of the best places on Earth for observations. So my second question, please. I mean, you talked about the ground-based telescopes. What about the space gamma ray telescopes? Do you plan to work on this as well?
Well, here in Adelaide, we are not involved in the space-based telescopes. But the nice thing is that, so for example, the Fermilab I was talking about is operated by NASA, and all the data are actually publicly available. So if you're interested in doing something with Fermi, you can basically just get the data. And I was doing some research with Fermi in my PhD thesis. So Fermi is, every few years, they are publishing the newest catalog of gamma ray sources. The latest one has over 3,000 objects, and they also do a major effort in actually determining what kind of source the object is. So if it's an AGN, if it's a supernova remnant, a pulsar wind nebula, and they identified maybe 1,500. So there's still like half of it where we don't know what it is. And what I did in my PhD thesis, I was trying to connect the Fermi data, the gamma data, with other wavelengths, and then using machine learning to find out if it could be an AGN. So in that part, I was doing a bit of Fermi. But yeah, if any of you is interested in using the space-based data, it's available. They are the catalogs, but you can really also download from a specific region of the sky. You can download the data, and they have the software if you want to do some dedicated analysis. Yeah, so that's really nice.
That's great, and this is one of the points that we want to encourage our postgrad students here in our university to collaborate with. And since you mentioned that the Fermi is providing huge amount of data, they can, you know, they can analyze it, study, make projects, and which is really great. But as you mentioned, we still need to work on these objects and the universe. There are lots of objects which are still we want to dig behind their origin and how they formed and their physical characteristics. Thank you very much.
Thanks.
Any questions, my friends, for this amazing and nice lectures? I am very happy to know that Gamma Ray has a huge interest in the universe, especially, you know, with the intergalactic or galactic plane, and also the Crab Nebula. Crab Nebula is one of my favorite objects in the sky. So let's see. Any questions, Dr. Aid?
Yes. Well, there's one question, why Chile? So there was a major, I think it started 10 years ago when the first idea about CTA was popping up, that they were searching for sites. So there was a major search. So we had potential sites in Chile, in Mexico, in South Africa, or in Namibia, also in Australia. So all over the world, there were these potential sites, and they were performing measurements, for example, from the atmosphere. But then they were also assessing how the weather there is, and if there are some, for example, hurricanes and other dangerous things. So, and also how is the infrastructure, and are we getting financial support from the host country? So yeah, all these factors were assessed, and they were writing a huge paper about that. And then in the end, it went to Chile, actually, because we got a huge support from the ESO, from the European Southern Observatory, which is in Chile. Just from the side, actually, Namibia was the best one, and Chile was just behind that. But yeah, because of the support from ESO, we decided to go to Chile.
Yes, excellent. I agree with you. It's one of the best places on planet Earth. Actually, at certain point, there was an idea to construct one of the gamma ray telescopes in Saudi Arabia, in Jabal al-Lawz in Tabuk. This is nearly 2,000 meters and very bluish sky and very nice sky for observations. And one of the telescopes we were thinking of was gamma ray. So we need to make a brainstorming session with you and Rami about this collaboration.
Well, if you have some funds, maybe we can put just one telescope there, because actually that's an important thing, because we can only measure during nighttime. So if there's some transient happening during daytime, we can't measure it. So if we would have telescopes around the world, that would be a nice thing. So it might actually be interesting to maybe put one in Saudi Arabia, yeah.
And you know, in Saudi Arabia, the clouds, nearly, we have a clear sky around 300 nights per, per year. So very good. And there, especially in this mountain, Jabal al-Lawz in Tabuk, in the north of Saudi Arabia, high mountain and very clear sky. And for almost 90% of the year. So I think it is one of the best sites around here.
Sounds good.
Yes, thank you very much. Any questions? Do you hear me, guys? Dr. Jamal Madani. Also, I have a question for Rami, please.
Yes.
Rami. Okay. You made an interesting talk. Nice.
Thanks so much. I appreciate it.
Nice. Piece of art with Dr. Sabrina and the rest of your supervisors, actually. Regarding the galactic plane, you said there are about 86 objects, and there is still about 40 unknown, not non-identified sources.
Yes,
is that right? 40 unknown objects.
I will try to show the slide here.
Yeah, please. The observations was from HIS and CTA, was it?
No, only HIS.
Only HIS, okay. Sorry.
So okay, let's have the slides. Okay. Are you seeing the slides?
No, I see your Wikipedia.
No, this is okay.
Okay, that's different. There is something else going on in my computer. Yeah, I'll show you in. Where is it? Yeah.
You can find this recorded meeting. في سؤال هنا برضو بس ما ادري.
I'll present this one soon. There is a difference going on with my preview. Okay. Yeah, I'll present it. So as I mentioned before, there is a.
Go ahead.
There is 76 sources from HIS, more than 76 sources from HIS, which is been observed by other, which has been observed by, HIS on the galactic plane. So these sources usually have their potential to be pulsars, winds, or something related to this. So as we see here, which is so there is some well-known sources. احنا عندنا معلومات عن بعض الأجرام السماوية مثل الكراب نيبولا. Crab Nebula, well-known source because we've seen it in all the spectrum. So we've seen the Crab Nebula in X-ray, radio, and ultraviolet and optical. So احنا نعرف الأوبجكت هذا could be producing gamma ray. السوبرنوفا can produce gamma ray. ولكن بعض الأجرام السماوية اللي موجودة في الجلاكتيك بلين have their mystery. يعني احنا عندنا 76 source هنا. بعضهم they have their own mysteries. بعضهم supernova, بعضهم pulsars من nebula, بعضهم binary systems, يعني two stars rotating around each other, taking energy, black holes with the stars. So each one of these sources have their own origin. يعني ما نعرف عن كل الجلاكتيك الهاي انرجي جلاكتيك بلين كل شيء. فهم رصد الهيس اوبزرفيشن سوت رصد للسبكترم للجلاكتيك بلين سيرفي كامل. فالرصد هذا اعطانا النتائج هذه 76 source. We are sure with a confident level of 5 sigma. بس احنا ما عندنا معلومات عن ال 76 source كامل. احنا عندنا معلومات عن ال 8 supernova location. We are sure there is supernova there. We've been observed it with multiple spectrum. يعني احنا شفناها radio, X-rays and stuff. So احنا متأكدين انه هذه supernova. So when we see it in His with high gamma ray, and we see the morphology similar to the X-ray, which is also considered a high energy, that means both of them related. They are the same source. But we have 11 source as this gram from 2018 have no association with anything else. So they're mysterious. ما عندهم association. There is indication, but there is no solid evidence. في indication, ممكن في pulsars there, ممكن there is supernova there, but المورفولوجي حقت السوبرنوفا بين اكس راي تختلف عنها في الجاما راي، فما نقدر نقول الشكل حقهم مو زي بعض، فما نقدر نقول انهم هم نفسهم. لكن ال 8 supernova detected we have an example before mentioned اللي هو ال 8 supernova مثلا الكراب نيبولا موجوده في الاثنين، فهي واضح انه هذا نفس هذا. ف we have solid conclusion from the morphology and the energy. احنا عندنا المورفولوجي واحنا عندنا الانرجي السبكترم the energy spectrum for the source. خلاص يعطينا هذا الدليل انه هذا السورس already انتج الجاما راي هذه through the production method that Sabrina mentioned in her lecture, right? The production method of proton-proton collision or quantum scattering or other process. فعندنا indication لبعض السورسز، بس بعض السورسز احنا ما عندنا indication لها، فانا ما نقدر نجزم انه مثلا عندنا هنا 11 sources not associated و 36 not firmly identified، يعني ما هي 100% معروفة. فهذه still have a question in them، يعني لسه السؤال مطروح ايش المصدر حق السورسز هذه، والى الحين الابحاث تنتج كل يوم على السورسز هذه.
جدا جميل.
دكتور ياسين.
تفضل دكتور عبد الرحمن ملاوي. he has a question and a comment please. دكتور صابرينا.
Thank you very much, Dr. Yasin. Thank you to Dr. Sabrin and to Mr. Rami for this wonderful talk. I was about to ask if the gamma rays objects are associated with other objects, but I think Rami already answered the question. But my question is, do you have any idea about the mechanism that is behind this gamma ray radiation? And also the other question is, how are you going to use machine learning in your project of identifying gamma ray objects? Thank you very much.
Very good question, Dr. Abdurrahman. Dr. Sabrina?
Yeah, so regarding machine learning, in the reconstruction of the events, we often use machine learning. So we are interested in the energy and the direction of our incident particle. And actually, we're also interested in what kind of particle it is, if it's a gamma ray or a hadron. Because as I said in the beginning, both particles are creating these air showers, and we just naturally measure both event types. So when it comes to these event types, that's a typical classification approach, and you can use random forest to distinguish between the gamma ray and the proton events. That's one thing. And then we have this indirect measurement technique. So, which means we're only measuring an image of the air shower. We are not measuring the actual particle. We are measuring light from other particles. So we somehow have to infer from this image the energy and the direction. And for that, we can also use machine learning. For example, to reconstruct the energy, it's basically a regression. And you can use random forest, for example, also to perform a regression. And the same is true for the direction. So that's one thing, just in general, for reconstructing our events. And then, as I said earlier, in my PhD, I was using machine learning to discriminate between the different source types. So talking about blazars or AGNs in general, they will have different spectra, for example, or other features in their spectrum that are distinguishing them from other objects. So that's another application of classification methods. But you can also use them to actually enlarge your simulation sample by using generative networks, or to getting a bit more fancy with these methods. But you can also use, deep learning is a big thing right now. It's actually a lot of applications for machine learning, also because we have big data and we somehow have to reduce our volumes, and so lots of different applications for that. In general, in astronomy, I think we could really use a lot of machine learning to find out interesting things, and actually also there are also methods to search for unusual events. So also just in astronomy, I think we could apply that and then look into these unusual events. And then the other question was about
the mechanism. What is the mechanism? Do you have any idea about the mechanism of what is generating, these gamma rays?
Oh, it all depends.
Are they thermal or non-thermal? For the...
Oh, we're talking about non-thermal here. So in high energy astrophysics, we are interested about the non-thermal radiation. So depending on the source type, there are different processes where they can be produced. Typically, we talk about, or we distinguish between hadronic and leptonic scenarios, where they can be produced. So, for example, they can interact with the ISM. You have proton-proton collisions, and they can then go to gamma rays. They can also, I don't know, I might have a slide somewhere, but they can also be produced by synchrotron radiation and then upscattering. So that's another bigger topic. And then depending, as I said, on the source, there are different processes where we think where they're coming from. So, for example, Rami was talking about supernova remnants, and we have the shock front where we have lots of particles, and the protons, for example, can we can model the proton spectrum in the supernova remnant. From the proton spectrum, together with ISM measurements, we can model the gamma ray that we would expect, and actually model a morphology, which is also something which another student here is doing. So we have a very precise measurement of the ISM by the MOPRA telescope. That's a radio telescope here in Australia. And with this very high resolution map of the ISM, together with the idea we have about supernova remnants, we can actually simulate or model the gamma ray morphology, and we can then compare that to our observations. And then by changing the model parameters, we are trying to find out what processes actually powering this specific AGN, if it's a hadronic scenario or a leptonic scenario, if it's really an SNR, or if it's maybe powered by a parts of wind nebula. And then also trying to figure out the model parameters. For example, if it's a slow diffusion or a fast diffusion in the shock process, and what the energy budget in total is of this SNR. So these are different things that you can try to find out.
Very interesting. Yeah, thank you. This is encouraging also for our students to, regarding as far as the first part of your answer regarding the machine language.
There's a lot of interest these days.
These days, and lots of data.
Even me, I'm interested in this. Hopefully, I will try to do some.
And it's very good for finding jobs after uni, I think.
Absolutely, it's encouraging, and we have a great amount of postgrad and undergrad students who are looking for jobs. So this is very enthusiastic. Great, thank you very much for the answer. One of the questions, lots of my students and the department students, they wanted a copy of this recording, and it will be available via the department channels, and they like very much your lectures, Dr. Sabrina and Rami. There was a comment, I think, by Dr. Jamal Madani. He wanted to ask. Is he still there, Dr. Jamal? Can you send the question, or are you still there?
أيوة دكتور السلام عليكم.
سلام لك دقيقتين يا دكتور.
لا أقل من دقيقة. It's a question for everybody. In fact, it's not a question; it's an idea. Is there any observation, or is it possible to observe Cherenkov radiation produced by cosmic gamma ray in interstellar medium or in atmosphere of other planet?
This is a deep question from a physicist.
An old layer cosmic. In fact, I studied cosmic ray with Dr. in Durham about 1980 something.
In the last century.
Sorry. Well, to reduce Cherenkov radiation, you need atmosphere, or you need a medium that allows the production of Cherenkov radiation. So if you find a planet which has an atmosphere, you should be able to. Actually, Cherenkov radiation, or you don't necessarily maybe need an atmosphere. An alternative might be water or ice, which is something that, I don't know if you know how neutrinos, or how we detect high energy neutrinos. We do that actually in water or in ice. It's the same principle as in gamma ray astronomy. Neutrinos going through ice, interacting, and they will produce Cherenkov radiation. And because water or ice is transparent, you can have detectors in the ice or in the water to measure that. And it's the same principle to measure neutrinos. So if you have something similar to that, and you find that, you could in principle do that. But I think it's a bit of the effort is maybe a bit too large to build a telescope on another planet, I guess.
That's interesting. Did you get it, Dr. Jamal? It was very clear. I have a question also from a friend of mine, a professor. He said, Dr. Sabrina, did you come across with semiconductor detectors for gamma ray spectroscopy that may be mounted on space telescopes?
Well, the camera that we have, or that we are using, it's not a CCD camera. The camera, or every pixel, is a photodetector. So in the current telescope, so MAGIC has, I was talking about every pixel is a PMT. Mm-hmm. For CTA, we are now looking into silicon PMs, actually, which is semiconductor photodetectors. So, and they have quite a few advantages, because PMTs are often sensitive to aging, and you need high voltage to power the PMTs. And then they are very sensitive to light. So you have to be very careful when the night sky is very bright, or if there's the moon. So Hess and MAGIC, for example, they have to shut down observations for 4 days when there's the full moon, because it's just too bright and we don't want to damage the PMTs. And during these 4 days, a lot can happen.
Yeah.
And it happened that there was a super interesting event and we couldn't observe because of the moon. So using the silicon PMs would bring these advantages. They only need 100 volts to power. They don't care about bright light. We haven't detected any aging, and they are getting cheap and very small. And I was talking about this small size telescope, which will be equipped with more than 2,000 pixels. So it actually means 2,000 silicon PMs that it will be equipped with.
Yeah, that's great. It is really very fruitful day here in our community, in our astronomy gathering, and also in your night sky in Australia. Thank you very much indeed. Was very happy, very pleased for this fruitful information and very useful. And we open channels of collaboration. We already with Rami, he is there. He's the first messenger. So next will be followed. And we try to contact each other regarding the idea of the Tabuk Jabal al-Lawz gamma ray telescope. It's a good idea.
It will be interesting because going with these collaboration, الارصاد الفكره حقتهم انه الحين حتى في استراليا هنا we have Simon that work in construction some telescope in Australia. هو قاعد يفكر انه شغال على موديل انه ايش يصير لو ركبوا تلسكوب في استراليا وايش يصير، ايش الارصاد اللي متوقعين يشوفونها وايش يحتاجون، بحيث انهم يضيفون التلسكوب هذا with CTA اساس يكون في collaboration for all sky all time. نفس الايفنت هورايزن idea، نفس الحركه حقت ايفنت هورايزن. They have many telescopes that can cover all the sky. Yep, cover all the sky all the time. So إذا كان عندك سوبر نوفا صايرة في الوقت وعندك ايفنت وصار في warning، كل التلسكوبات اللي عندها ليل تقدر تشتغل وتقدر ترصد الجاما راي اللي منتجه، ونعرف ايش قاعد يصير في السبكترم حق الجاما راي من initial supernova until it's come down after like a long time.
Interesting. Thank you very much. Thanks a lot again. And you know, the 90 minutes almost pass away very quickly because of the interesting talks. Thank you, and hope to see you again, and very happy to see you guys. Thank you very much.
Thanks.
Bye-bye.